Hello, in this exercise we will study the control and operation of point-to-point HVdc transmission links and we will try different control modes for the converters including grid forming controllers and VDCQ and also PQ. Let's open the parameter files. Actually we don't need to open it, but it's good to open to see what is inside the variables which are defined here. We don't need to even open it because of the initialization that we do in the Simulink file. So after opening, if we go to the workspace, we can see that the parameter file is already run from Simulink. So in next step, let's check the control mode of the converters. PQ converter 1, VDCQ converter 2, and also the reference selectors stepwise for active and reactive powers. So everything looks good. Let's run the model and make it faster, 10 times faster. So the video is now very fast. In the next step, we need to look at the result scopes and discuss a bit about them. So by following the signals, we can see how each converter is behaving. So for reactive power, we can see that converter 1 and converter 2 can control the reactive power independently. So there is no link between them. The next question is, can we determine from here which one is PQ? Yes, if we look at the powers, we can see that converter 1 is actually following the reference value of the power. So it means this converter is in PQ. The other way that we can do is we can zoom in the DC link voltage, and in DC link also we can see converter 2 is exactly same as the reference value for voltage, and the other converter experience a voltage drop which appears between the reference value and the DC voltage measured at the terminal of this converter, which is converter 1 in this case. Also, we can compare the impact of active and reactive power on DC link. Apparently, the active power is related to DC link because the DC link voltage is affected by the active power, which is stored in the DC link capacitor as a static energy. Here also we can see that when there is a step in active power, we see this transient on the DC link voltage. But for example, if we look at t equal to 3.5 second, that is also 1 per unit of a step in reactive power, but the impact on DC link voltage is much smaller than that of the active power. So we can see these two big transient in DC link voltage are due to the steps introduced in the active power reference. So we can say the impact of reactive power on DC link voltage is negligible compared to that of the active power. In the next step, let's save the result that we got from this simulation. Yeah, we can copy to clipboard. This copying to clipboard is better because it will change the background color of a scope. Otherwise, we can take the screenshot, but it will be with that black background color. Then in the next step, let's swap the control mode of the converter. So now converter 1 should be in VDCQ control mode and converter 2 in PQ control mode. After running, we can see it's working properly also in this case, but if we compare the result in this case with the previous one, we can see that now converter 2 is following the set points of the power, and now the power flow is reversed. But for the reactive power, they are independent from each other, so each one can control its reactive power independently from the other one. So We don't see any change in reactive power responses. And also for DC link voltage, we can see that now converter 1 is the one which is matching with the reference value of voltage, and not converter 2. The next step is to compare the responses of DC link voltage in these two cases in a more detail. If we compare them, we can say that the transient behavior in DC link voltage is the same in these two cases, except that now converter VDC of converter 1 is matching with the reference, while in the previous case it was reversed. But apart from that, the transient behavior of DC link voltage looks similar, and yeah, we can reproduce the result from previous case with this new setup of the model. For that, we simply can inverse the sign of power references, so the power flow will be inversed in this condition, which means it will be similar to the previous case. I mean the first case that we had in this exercise. Now in both cases, converter 1 experienced this a step down at the beginning and then a step up at t equal to 2 seconds. For reactive power, we don't need to do anything. We have reproduced the previous result, but the main difference is that the transient of DC link voltage is also inversed. And the reason is that in the first case, we had this step down in power, which means that we were injecting power to DC link, considering the power sign convention that we discussed in the previous exercise. And also later, when we introduce this step up in the power, we are extracting power from the DC link, which leads to this voltage drop during the transient. But in this case, in the current case, we have a step up at the beginning and a step down at power afterwards, which means we will have a voltage drop first, and then the DC link will experience this over voltage afterwards. So what will happen if both converters are in the same control mode? Yeah, apparently it will not work. We can test it on the model, but the problem is, for example, if both of them are in PQ control mode, who is taking care of the DC link voltage, or also if both of them are in VDC control mode, you don't have any control on the power flow. We cannot transfer any power. For example, here we can see that when both of the converters are in VDC control mode, it looks that it is working, and yeah, we can provide this reactive power on the AC side of both converters. But there is a trick here. The point is that there is no or very limited power flow on the DC link, so there is no voltage, and both of the converter are controlling the voltage to the same level. But for example, let's say for any reason, the reference value of the DC link voltage for one of the converter is 0.9 per unit, then we can see that it's not working. There will be some a strong interaction between converters, which leads to stability problems. So now let's remove this gain and test the model when both of the converter are in PQ control mode, and run the model. We expect that in this case also it becomes unstable. So you can see that neither power nor DC link voltage is controlled properly, and the system is not working. And it doesn't matter, it's, the sign of the power reference doesn't matter. Even if we remove that -1 just to test it, you can see still the system apparently will not work. Yeah. Before going to the next step, we need to learn how to visualize result of different simulation on the same plot, because as of my knowledge I don't know how to do it on scopes, and I imagine there is not that option on the MATLAB scopes. Maybe in future versions it will be available, but there is another cool feature in MATLAB that we can use for this purpose. For that we need to log signals, but if you, for example, click on data inspector, it will provide a simple instruction for using this feature. We need to log signals first, and in the next step run our simulation model, and finally the data will be saved on the data inspectors in this area. So we will find the signals here, and we can plot them by selecting the correspondent signals. So we already log the signals in this model, which are active power, reactive power, and DC link voltage. But for example, let's show it how to do it. We can log the signals in different ways. One way is to select the signal and then go to this log signal. Then the selected signals will be logged. When we log the signal, we can use this radio sign to open the data inspector window if you want. And also we can right click on the signal and then choose this log selected data. To remove the logged signals, we can use both ways. You can see that in this model, the active and reactive power, also DC link voltage are already logged. So, but in case they are not they are not logged in your model, you can use the method that we just explained. Now let's run the model and see to the look into the data inspector. We can see that the data are not available. The problem is that we need to configure the log signals. So go to this data export and activate signal logout. Now it is activated, and after running the model, the signals that we have selected will be available in data inspector workspace. So here we can see the signals, active power, reactive power, and DC link voltage. We can remove the signals by selecting each of them, but another thing which is important, I guess, is to limit the the number of runs that will be saved. In this simulation, 2 is the best because we are going to compare 3. So the first thing is that we need to run the model for changing the bandwidth of active power controller. First, let's make the converter to VDC controller, so we know, and also introduce a step in the DC link voltage. The rest should be fine. Now let's go to the parameter files and divide the active power control gains by 2 to make it 2 times slower, and run the model. Yeah, after running the model, we can see the new variables are logged in the data inspector, and it is called with run 2. The previous run is archived now, and it is run 1. We can choose the signals from both run of the model to observe them on the same plot. We can also remove these archived signals in this way. Yeah, then now let's run it with the default value of the control gains for active power. And finally, for splitting off the controller by multiplying the gains by 2. So now we have run the model with 3 control gains, run 2, run 3, and run 4. We can see here. So for example, we can observe the response of converter 1, response for active power of converter 1 on the same plot. Let's change the format of the signal so we can distinguish between them. So from the result, we can see the impact of changing the control gains on the active power response. In the first run, which was run 2, in this case, this is the dotted line, we can see the response is slower because we made the controller slower, and we have the default, and also when we increase the speed, we increase the speed of the active power controller, we can see the response is faster, but it introduced some overshoots in the response also. We can observe the response of converter 2. That should be the similar because converter 2 is in VDC control mode, and it is simply balancing the power in the DC link. So whatever power is injected, the other converter is extracting or injecting if necessary to balance the power. So they will show a similar response. Also, it's nice to observe that this 2 times faster or slower really makes it to look like 2 times faster on the control response also. For reactive power, we don't expect any change because we expect that they are decoupled. There could be some small impact from the active and reactive power controllers on each other, but it should be negligible. Now for easiness, let's make all the signals from each run with the same format. This one. You can do it the way you like, but yeah, I think it's easier to make each run the same because we want to compare the signals from different runs. So yeah, for reactive power, we see that there is no impact as we were expecting, and also for converter 2. But for the response of the DC link voltage, we expect some impacts because the DC link voltage and active power are directly related to each other. Here we can see when the controller is slow, the overshoot, the voltage drop or the transient in DC link is also smaller and with respect to the default one. And when we increase we speed up the active power controller, we see that it's somehow the DC link controller face some saturations because it's not fast enough to inject the required active power immediately. Yeah, so this was for active power. In next case, we are asked to do it for DC link voltage as well. So let's divide the control gains by 2 to make it 2 times slower and run the model. Now for the default value of gains, run the model. So we don't need to run the parameter files at each time because we use this initialization feature of Simulink. We just need to change the data here, save it, and run it. Now we will have the result for the 3 cases, and since we limited the number of archives in this configuration, we can see the result from our the previous case, which was for active power, is automatically removed. Yeah, it's removed, and I think apart from this saving the memory storage of your PC, that makes it the comparison much easier. If we take if we can't we change the configuration as we did here for 2 archives, for example, or for any other study, you can choose the right number of archiving. So let's make the format of each run similar to each other. Now this is for VDC gains. So we expect to see the impact also on active power, but mainly on the step in DC link. If we zoom in, we can see that there are some oscillations. When we increase the bandwidth of the DC link controller, the impact of making it 2 times faster or 2 times slower is not visible in this case, because DC link control loop is not really linear, so it's a bit more complicated, but you can see the impact on the oscillations. Then for active power, when the DC voltage controller is slowed down, uh, we experience this overshoot, and with the default gains we don't experience, which means there is no interaction between these two controllers. And when we speed up, the impact is not that much, because the interaction of the two controllers is already removed by the default gains. So further increasing the speed of DC link voltage controller doesn't impact this interaction between these two controllers. The important thing here is that to understand, the DC link voltage controller should be faster than the active power controller, because the active power controller is injecting power to DC link or extracting, and DC link voltage controller is reacting to this change. So it means it should be faster to be able to track the change in a smooth way. Also, you can look at the other points and see the transient in different uh, operating points and different conditions. For reactive power, we don't expect that much change, because there is no really a physical link between reactive power and DC link voltage controller. There could be some impacts, but mainly because of the imperfect decoupling of the control loops. But physically, there shouldn't be any relation between DC link and reactive power. In final case, we are asked to change the control gains of reactive power for converter 2. So let's change it here, because the gains are used for both controllers, if for both converters, if we change it from the script. So here let's slow down it by dividing by 2 and run the model. We could use the similar method and change the control gains for active power and DC link voltage also from this dialog box of the converters, but yeah, we did it the other way, so you could see both cases. Yeah, and finally for 2 times faster. Now we can open the data inspector window and see that the data are logged here, and the previous runs for DC link voltage controller are automatically removed. So we know that these signals belongs to the change that we did on the reactive power controllers gain. Now we make the similar format. We choose similar formatting for each run. Also, we can change the names here if you find it useful. For example, this one we can slower queue and with the provided gains. This is or faster queue. In previous cases, I was using the number of the run, so I knew that the first run was slowest, and then provided, and then fastest was the last run. In this case, we can look at the responses of active power. We don't expect that much change, but there could be more interaction with when we speed off the reactive power controllers. So here you can see that it introduces higher transient on the reactive power, but the difference is not much. It's because it's mainly due to the interaction between the active and reactive power controller loops. So you can observe the signals and investigate the impacts. The main change here should be on the reactive power of converter 1. If we zoom in, the impact is obvious, and we can see that this speeding of the controller really reflects on the result, and this makes it twice faster or twice slower. And finally, we can see the impact on the DC link voltage. We don't expect any change here, except for a small change in the transient, which is due to the interaction again between the two control loops. In this way, we can compare the result for different runs in the Simulink, and also as we did here for the changing the bandwidth of the controllers. Let's make it default gains for the rest of the exercise. And in the next step, we are asked to implement the grid forming controller inside one of these converters. So let's implement it for converter 1. We can implement it for the other converter also, but doesn't matter. If we go inside, we can see it's uncommented. So let's make the control mode of converter 1 to grid forming. So it will be activated and highlighted, and the blocks will be in a bold color, not gray ones. Inside this grid forming block, which is already provided to you, we even have the inputs and outputs. Let's begin by obtaining the angle or omega t from frequency. We need to multiply it by 2 pi to make it the angular frequency, and also you can look at the setup of discrete time integrator. The output will be omega t or theta or angle of the frequency. Now in this case we don't need any PLL because we are dictating the frequency because this is a grid forming. Now based on this angle that we obtain from frequency, we can convert the ABC voltage to ABC DQ0. We don't need 0 because we consider it's a balanced system. But we need this UD and UQ component of the measurement voltage. In the next step, we can also label this UD and UQ references. Then we need a voltage controller to control the voltage, because this grid forming is controlling the voltage and also dictating the frequency of the system. So for controlling, we need to compare the reference value and measured signal. Before getting the from this go-to block, let's change the format. The good thing about changing the format at the beginning is that when you take this from blocks from the go-tos, the color and the format will be also copied to the derived blocks. We do the comparison for both D and Q axes. Then we need a PI controller to control the voltage in a discrete time with a sample time of Ts, and the controller is PI. For the gains we use the gains that is mentioned in the exercise document. Here in the list you can see KPI UAC and KPI UAC of HVdc. The other one is the one which is available in the workspace, but the one without HVdc is the one which is available inside the block, which is coming from the dialog box of HVdc. If you go back and watch the module 1 exercise, I have explained the difference between these two cases in there. After that, the output will be the reference of D and Q voltages. We can transfer it to ABC domain by this DQ ABC transformation and use the same omega t or angle, and the output will be the reference voltage which is sent to the converter for generating this voltage. Also, we can add a scope here just to observe the voltages and frequency. So one for D-axis voltage, reference and measurement, and another one for Q-axis voltage, and finally we have one for frequency. When we duplicate these input ports, the input signal is connected to both of them, and we don't need to use or connect them by wire or go-tos. Also, we can measure the frequency of the voltage to compare these signals, then format the input ports and make them orange, and also for the output ports we can use green. These are just formatting. And let's rearrange a bit the blocks and also change the format of the scope. Also, we can label the signals. So when we look into the scope, we can see the signal names for a better understanding of the result. UD ref, UD measurement, and also for and also for UQ and frequency. But we also need to modify the setting of PLL to make it 50 Hz and also discrete with introducing this sample time. Now let's remove the grid and check also the control mode of the converters. Everything looks fine. We can see that it is working. There is no stability issue at least. But to interpret the result, we can say converter 1, which is in grid forming control mode, is not following the reference for reactive power, but converter 2 is still in VDCQ and is able to control the reactive power to the set points. For the voltage, is converter 1 which is controlling the voltage, but they are matching. Both of them are the same because because there is no active power flow in the DC link, so there is no voltage drop on the DC link, and this the change in the reactive power of the converter 1 is introducing some transient which can be observed on the DC link voltage and also on the powers because of the interaction between controllers. We can look into the signals of the grid forming controller that we implemented from the scope that we added in this block, and using the legends we can see that UD is following the measurement. There is a delay, but it is following, and also this ramp in the UD is introducing some transient on UQ and also frequency. If you want to see how this reference value for UD is defined, we can follow the signals and see that there is a step introduced in the voltage, and that is why we see that the reference is going up, but it's not like a step because we introduced this rate limiter, so it is limited. Finally, let's look at the voltage and current of the converters. On the left side, we can see the voltage and current of converter 1, and on the right side is the voltage and current of converter 2. For converter 1, we can see that the voltage is formed by the grid forming converter, as we can see on the top plot. But the current is 0 because it is an open circuit. On the other side, the voltage of converter 2 is 1 per unit in the whole period of time because it is connected to another AC grid. And the current, we can see the current is flowing in this case because of the reactive power, which is which this converter is providing or absorbing from the grid. Now in the next step, we need to add a resistive load and connect it to this grid forming converter. We can use this RLC branch 3-phase and also a ground to connect it to the ground. Then let's make it R, and the value should be, because we want to have 0.5 per unit of active power, so it should be 2 multiplied by voltage to the power of 2 divided by the rated power. So the value of resistor should be twice that of the base value of the impedance. Now let's run it, and here we can see that we have the current also on the for converter 1, and the current is exactly in phase with the voltage because it is a resistive load, and the value of the current is 0.5 because we wanted 0.5 per unit of active power. And for converter 2, we can see that this current is injected to the other AC grid, so we have similar behavior, but on top of that we have additional impact from the current for reactive power. We can look at the active and reactive powers also. None of the converter is following the reference value because one of them is grid forming, the other one is VDCQ. For reactive power, converter 2 is following the reference, but converter 1 is not because it's grid forming. And in this case, it is 0 because there is no need for reactive power. And also for DC link voltage, you can see the impact of voltage drop in this case, that there is a difference between the DC voltage at the terminal of two converters. The system is behaving as we were expecting, so the voltage is formed on the AC side, and the current is flowing, or current is injected to AC grid. In this case, it was a resistive load, and so the power is actually being injected from DC link to AC grid. You can also explain the sign of powers on the resultant active powers. In the next step, we are asked to connect this wind turbine to the grid forming converter. So let's connect the wind turbine, and also always be careful about the phases. Phase A should be connected to phase A, and B and C. And here we have the step at 1.5. Now the simulation is probably a bit slower because we added this wind turbine model as well into the model. We can see that it is behaving properly, and the voltage is formed, and also a current is flowing, but the amplitude of current is smaller than 1 per unit. That is because the base value of wind turbine is 400 megawatts. You can find it in the script, and also on the dialog box of wind turbine itself, it is visible. While the base value for the HVdc converters is 1200 megawatts, which is 3 times more than that of the wind turbine. And if you want to see where these plotted powers are measured, you can follow the signals and see that they are coming from the converters. So these per unit values plotted here are respect to the base value of HVdc converters. For reactive power, again, the converter 2 can follow the reference signal, but the reactive power of converter 1 is defined based on the required reactive power for maintaining the voltage at the AC side. So in this case, we have this wind turbine, which includes transformer and some inductors in between. That is why we see a non-zero reactive power. And finally, for voltage, it shows a similar response with some transient. For the voltage and current, you can observe them here and also interpret the amplitude of current. We observe some transient before wind turbine starts to generate the power. If we open the dialog box of wind turbine, we can see this connection time, and that is exactly the time that wind turbine is connected, and it is introducing these transients. If we want to connect the wind turbine from the beginning, we can try it, but it doesn't work. If we look at the scope after running the simulation, you can see that it becomes unstable. So let's bring it back to the default value. So we can say that we cannot connect the wind turbine before the grid is formed by the grid forming converter. Maybe if I show you a part of one of my presentations about grid forming converters, maybe it becomes a bit more clear to you. So let's look at it. I tried to explain it in a metaphoric way, and it might help you to understand the concept in a more intuitive way. In classical or conventional power systems, we have these synchronous generators, which are like a foundation of voltage and frequency. So they are keeping voltage and frequency, and renewable energy sources can rely on this voltage and frequency to control their active and reactive power. If the share of renewable energy sources increases, and on the other hand, some of the synchronous generators phase out from the system, it means that the foundation of this voltage and frequency is becoming smaller, and on the other side, the size of the renewable energy sources like wind turbines is getting bigger. So probably the foundation is not anymore strong enough to maintain the voltage and frequency, and we are at the risk of voltage and frequency collapse, which means that the renewable energy sources are not able to control their active and reactive power properly and lose the instability. One solution for that is grid forming control schemes to support voltage and frequency in the system. So this kind of renewable energy sources which use grid forming control schemes, they support voltage and frequency as well as controlling their active and reactive power. So the foundation of this voltage and frequency is stronger, and the grid following renewable energy sources, they can rely on that for controlling their active and reactive power. But in this case, we are studying a very special case, which is offshore wind power plants. In offshore wind power plants, actually, there is no synchronous generator, so we can remove it. And this example should look like something. These renewable energy sources, which are supporting voltage and frequency, in our case, will be HVdc converters. And let's say they are not controlling their active and reactive power. Actually, they are just balancing these powers in this system. So we have only grid forming control schemes, no synchronous generator, and the HVdc converter is supporting the voltage and frequency in the system. So the other Wind turbines are able to control their active and reactive power by relying on the provided voltage and frequency by HVdc link. Yes, so it's important to know that this is a special case, and that is why we actually can dictate the frequency in this case, because there is no other synchronous generator in the offshore system, and we can fix the frequency. Otherwise, we needed to add some droop to our controller to make the parallel operation of different generators possible. But in this case, we don't need it because the HVdc converter is the only component taking care of voltage and frequency. So we can say that the wind turbine should be connected actually after the HVdc converter is forming the voltage and frequency. At the end, you are asked to build this 3-terminal HVdc network and also try different control modes for the converters. I think that is a good homework. If you spend some time on it, it will give you a deeper understanding of these HVdc links. And that is end of exercise for module 9. Have a good day.